Well, hello again. We're back on track finally after a while. It's been longer than I expected to get to part 2, but I had a lot of things that needed to be done. God, I had so many things, and I didn't want to do them until I could actually apply, a focused attention to part 2. And I think we finally reached that stage. And I want you to know I'm really blown away by all the responses I got to this idea of taking a good radio and messing it up just to see what it'll do. It's great. I didn't expect that. Brendan said he was kind of surprised by the positive response also. He didn't, we expected a positive response, but not overwhelmingly positive like we got. Everybody seems to have chimed in for this one. Fantastic. I appreciate it. I'm glad to have you with us. A couple of items that were mentioned in the comments. Keith Jordan left a really good comment. It was a long one. It was very I was surprised by it. I'm not sure I deserve that kind of good positive comment, Keith. I appreciate it though very much. Thank you. And Steel City had a question. He said, a while back, I restored a battery radio. We made a power supply for it, and it was a Silvertone 6044-6045, and Steel City wanted to know, Phil is his name, he wanted to know what happened to that radio. Not him, but I think a friend or an acquaintance of his asked him one day, what happened to that radio that guy was restoring? Where did it go? Well, it went back to the person who bought me the radio to begin with. One day I was at work. This is kind of a little refresher. One day I was at work. Our oldest grandson's wife showed up. She and a girlfriend had been shopping at flea markets and everything, and she found that radio. It was all messed up. One side was completely gone out of it, if you'll remember. She brought it where I work, and she said she was very, very proud of what she found. It was in some garage somewhere, all covered with dust. So anyway, I went ahead and restored it, and I thought it would be only appropriate once I got it operational and we made the power supply and got it working and everything. I thought it would only be appropriate that it went back to her, and it did. She enjoyed it. She said she couldn't believe it was the same radio. I couldn't believe it either. Anyway, that's where the radio is now. I have another one, Amberola 1B. He said part of our series I should maybe cover a little bit about how to use a multimeter. Good idea. You guys got some ideas, some inputs. You want to see something disconnected, to see what will happen. I'll kind of log them all in. We may not get to them right away. We'll get to them later. And yeah, I'll be happy to disconnect a short, to put a resistor across or whatever. Okay, it's up to you. And Tim wanted to know about using a fast blow fuse versus a slow blow fuse. We'll cover that. That'll come along. And Gordon Cole wanted to know, did the camera noise go away when the cap was disconnected? I don't remember. I guess we'll have to check that out. Do it again. No problem. But this time probably the camera probably won't even cause any noise, which would be just about the case. Actually, the antenna was picking up that noise and sending it through. So what do you say we get cranked up in part 2? Let's get with it. Let's find out what we're going to mess up today. Last time we proved that C5, which is connected to one side of the line, the power line coming in, we proved that capacitor can be removed and this radio will continue to play fine. However, it's designed to help eliminate, it doesn't eliminate them all like I said in the first video, but it's designed to help eliminate spikes that also come down the power line along with the 60 cycles. You get a lightning shot, 50 miles away or something, you're going to get that, static, and it's going to come in. It's going to come in the antenna. It may come down the power line. There's no telling. Something in the house may come on and off while you're, down your power line. There's no telling where it would come from, the spike, the high frequency spike, and it would go down through the capacitor to ground. So the question comes up, well, what's going on? Why would the spike go down to ground, and why does the 60 cycle keep going? Why doesn't the 60 cycles go through also? Matter of fact, why doesn't everything go down through that capacitor to ground? Well, it's called capacitance reactance. And here is the formula for capacitance reactance. X sub C. Capacitance reactance. That's what it's called. That's the symbol for it. And over here, it's 1 over 2 pi times the frequency times the value of the capacitor. If I increase the... Now, what is capacitance reactance? It's resistance. It's the amount of resistance between the plates of that capacitor, inside that empty space right there. Everything in the world has resistance. This also has resistance as well. And it's called capacitance reactance. Fancy names these guys put on some of this stuff when they first discovered it. Why they just couldn't put down capacitor resistance is beyond me. No. Anyway, you can see right here that if I increase the frequency, if the frequency goes up, it causes the resistance to go down just by this formula. See? And when the resistance goes down, guess what happens? That's right. It passes through the capacitor. Now, 60 cycles, the capacitor is designed, when they designed this circuit, that capacitor was designed not to let 60 cycles go through. It's too low. Low frequency, high resistance. Just the opposite. That's all I'm going to tell you about that. If you want to know more about capacitive reactance, look it up online. Also, there's a thing called inductive reactance, which is X sub L. Okay? X sub L. And that formula is a little bit different. Works basically the same. It does have resistance to AC current flow. And you can figure out the same thing when the frequency goes up or the frequency goes down, what happens to the inductive reactance, just like what happens to this capacitive reactance. That's it. We're going to move on from here. Once the current comes in and the rectifier, now this is what they call a half-wave rectifier. Half-wave rectifier. And it comes across and it charges first this electrolytic capacitor, goes through this resistor, charges this electrolytic capacitor, and it begins to smooth it out. Okay? Now let me show you what that half-wave rectified voltage looks like. Here's your old 60 cycle voltage coming down that power line. Once it gets rectified, the negative side, I've got the positive side on the top, negative on the bottom. Once it gets rectified by that tube, which in this case is a 35W4, the negative side is eliminated. So what we basically have, well not basically, but what we really have are positive humps with a space, positive hump with a space. Everywhere there was a negative, it's gone. It's not there. It just went away. So this is called half-wave rectification, okay? We have bumpy DC voltage coming out of that rectifier. It's called pulsating DC. It is pulsating. Now, had this been a full-wave rectifier, it would have taken the negative half of the 60 cycle waveform and kicked it up to the top, and we would have had, there would have been no spaces. We would have had just like that, lots of pulsating DC. Okay. Now here's the problem. This is very bumpy. We can't run this through to the plates of our tubes and everything. Imagine what the audio would sound like. We need to turn this into a nice straight line of DC. Well, how is that done? You know, we're halfway there. You know, we've taken 60 cycles and we rectified it. In this particular radio, we rectified it half wave, but we still got these bumps. They gotta go away. We've got to smooth it out. How is it done? Well, I'll tell you how it's done. It's done by these electrolytic capacitors. That's the purpose of an electrolytic capacitor, to take away the bumps and provide nice, steady, in this case 90 volts here and 110 volts here, to the rest of the radio, to run all the rest of the, you know, the plate voltages and the screen grid voltages and everywhere else that needs nice, steady DC voltage. The purpose of the power supply is to smooth it out and make it work with the rest of the radio. So what happens if we lose one of these electrolytic capacitors, or both of them? Let's take out one. Let's disconnect the ground on the first electrolytic capacitor. Now remember, this was the electrolytic capacitor that was in there initially, okay? And I took it out because it was having problems. It was a 75 microfarad and a 35 microfarad. Both of them were rated at 150 volts, working volts DC. And this radio was giving me all kinds of problems, so I had to get rid of this and put in some nice new ones. Now the nice new ones we put in are right there, those two black ones. See the two black ones? So what we're going to do is we're going to take out the larger of the two. We're going to eliminate the ground wire from right here, which is the 75 microfarad. Then we're going to turn the radio on and see what happens. So let me get that done. Well, as it turned out, it was easier for me to go ahead and disconnect the positive side of this electrolytic than this negative side, but it doesn't matter. It was taken out of the circuit. You could take away either end, you know, for the purposes of demonstration here. It's no longer connected to here, but I do have it connected with a gator wire right now because I wanted to be able to show you the before and after. Here I'm connected to the positive side of the capacitor, and over here I've got it clipped to the bottom where it goes through the circuit board and solders up. So let's turn up the volume and see what we've got with the thing in the circuit. Not bad, huh? All right, let's go ahead and remove the alligator clip, which takes the capacitor out of the circuit. Remember, now this is the first electrolytic. Hear that? That proves that the electrolytic is doing its filtering when it's in the circuit. I've heard this a lot in radios. I've had a radio played perfectly, and you know, here I was going through an alignment and everything, and all of a sudden it started doing this. The volume is down and it is garbled. And you know, previously it was playing perfectly. And I always went to the speaker. I said, man, there must be something wrong with that speaker. Well, no, I learned later on that it's a filter cap. Go to the filter caps first. You know, not to say that it's not a speaker, but always check your filter caps first. One more time, I'll let you listen to it. It's up to the maximum volume. All right, let's hook her back up now. You don't think those capacitors are valuable to the radio circuit? Yeah, it is. Amazing, isn't it? All right, let's hook back up the large capacitor and remove the second capacitor. See what effect that has. I now have the second capacitor removed and gator wired into the circuit just like we did the first one. Now we're talking about this capacitor right here. I removed it and it's gator wired back in, and we're going to pull it off just like we did the first one. So let's crank up the volume.
Football today on CBSSports.com and CBS Sports Radio.
All right, let's take off. Let's take it out of the circuit. Ooh, check that out. Hear that? Hear that? Ooh, you turn up the volume, see it? All right. How about them apples, huh? Now that's what you call motorboating, people. Motorboating. Okay? Let's hook her back up. Look at that. Look at it. It has more of an effect on the circuit. It has more of an effect on the circuit than the larger one did. This one here is only 33 microfarads. That one there I have in there is at 80. Amazing, huh? Let's do that again. That was fun. Crank up the volume. You get a little squeal. You get a lot of motorboating. Turn your radio on for the first time, especially if it's one of these little AA5 types, and you turn up the volume and you get this. Ooh, what is that? Well, now you know what it is, okay? Fantastic. Let's hook it back up. Nifty stuff, nifty stuff. We've still got our electrolytics gator wired in. However, the radio has gone stone dead on me. Look at here. No volume at all. Nothing. No tuning. Nothing at all. Maybe I blew out one of the tubes, huh? Let's find out. No, these tubes are all good. All the tubes are glowing. What about that one over there? Yep. This one glowing. Yes, they're all glowing. I don't see any burned resistors or anything. Nothing. No capacitors messed up. Let's turn the light on. What is going on here? The radio went stone dead. Yeah, let me take a voltage reading here. Alright, let's check the plate. Let's do some plate voltage checks here. Let's check the plate of the 50C5, which is pin 7. I think I've got this right. These things are kind of hard. I'm not used to working with circuit boards, but I think that's 1, 2, 3, 4, 5, 6, 7. No, that's 1, 2, 3, 4, 5, 6, 7. Let's see what we get. I've gator wired in the negative lead of my meter to the negative side of one of the electrolytics, because that's ground, okay? So we will go 1, 2, 3, 4, 5, 6, 7. Let's see what kind of voltage we get there. 0 voltage. 0 voltage. That's the output tube, the plate. Alright, tell you what, let's go back. Let's go to the 12BA6 or the 12BE6 and see what we've got on voltage there. Both of those are pin 5. Alright, we've got, let me see where our tube is here. I got so many gator wires, can't even find out what's what here. Alright, let's try the plate of the 12BA6. 0 volts again. We're not getting any plate voltage, people. Well, that means we're missing B+. And we're missing B+. Well, let's go over here and check the, let's check pin 5. No, let's check at the positive of the large capacitor and see what we're getting. That would be the 75. Put that there like that. 0 volts again. Ooh, my goodness. You know, now we just got done messing with these capacitors, these two electrolytics. And we now have 0 volts coming out of our rectifier tube. If we have 0 volts coming out of our rectifier, that means the 90 and 100 volts I told you about right here, that's not going to any of the plates. That's not going to anything up there. So we have somehow caused the voltage to stop coming out of this tube. See, I didn't change any components. I didn't change the tube. So the tubes are all good still. Let's see if they're glowing still. Well, that's kind of interesting. You know, we have no B+, but yet our tubes are glowing. Now, what the heck is going on? I'll tell you what. Let's go ahead. Let's take a look at this rectifier and find out what's going on. It was working just a few minutes ago. Let's zoom in here a little better. There we go. What is going on? We have the filament glowing, but the tube's not putting anything out. That's weird. Well, I'll tell you what. Let's take a look at the bottom of this 35W4. See what's going on. Let's do a little measurements down there. Well, here's the bottom of our 35W4 rectifier, and I'm getting ready to measure, and son of a gun, look at there. Look at that. See if I can get a little closer. That's one of the filament pins right there. Somebody has removed the solder from that pin. I don't understand that. Oh yeah, I do. Hey, I do. It was me. I removed the solder from that pin. Let's see what I did here. Let me back up a little bit. Where's the tube? There it is right there. Okay, I have removed the solder from pin 4. So that means that the filament's going to light. This half of the filament's going to light. See, that filament is center tapped. The voltage comes in, comes up through here, 117 volts. Comes up through here, goes down through pin 4, jumps up, goes over to pin 5, and provides the plate voltage for this tube. Of course, the rest of the filaments are fed through this half of that. Actually, I keep saying filament, it's a heater. The rest of these heaters are fed through the right-hand side of the tap. So when I disconnected this, yeah, the tube continues to glow. All right, let me get a little steadier hand here. The tube will continue to glow. The heater will continue to glow, but the center tap, I mean the left half that supplies the voltage to the plate is gone, even though you see a glow in the tube. Is that cool? So essentially what I did was I just cut that line right there by disconnecting it there. Let's solder that back up and see what happens. Alright, let's go ahead and test the voltage and see if we got the voltage back on our plate. Yes, we do. Yes, we do. We got 122, almost 123 volts. Let's turn up the volume and see if our radio's dead still. No, she's good to go. Good to go. Alright. Alright, now what we did here, now, I've seen this problem happen before. What happens is the left-hand side of the tube filament burns out, but the right-hand side continues to glow. But when this part burns out, you have no voltage to wherever it has to go. In this particular case, you have no voltage to the plate. So don't let that be fooled. Always check your plate voltages when you have a total radio failure. The first thing to do is check your plate voltages. Now, if you have an obviously burned resistor or capacitors blown up or something, you don't have to go through all that rigmarole. But if you don't have anything that looks bad, start with your plate voltages. Okay, I hope you... So one more thing. On this drawing here, on this schematic, this thing shows two... It depicts two separate heaters with a center tap between them. But if you go to the tube drawing in the tube book, actually what you have is one heater that's been center tapped like this. And this was the half that I disconnected right here. Okay? Alright, now let's see if we got any buzz out of my radio from my camera. No, she doesn't want to cooperate today. I figured that would happen. Well, that's it. I hope you learned a couple of things. That was fun. Next time we'll tear apart something else. Until next time, this is John.